Hey everyone, and welcome. Today, we're tackling a LeetCode problem called Find the Minimum Area to Cover All One's Y. It sounds a bit complex, but don't worry, we're going to break it down step by step into a really simple idea. Let's get started. So here's the task. We're given a grid, which is just a 2D list filled with zeros and ones. Our goal is to find the smallest possible rectangle that can completely cover all of the ones in the grid. Then, we just have to return the area of that rectangle. The key insight here is to realize what defines this smallest rectangle. It's not just any rectangle, it's the one whose borders are perfectly snug against the outermost ones. This means we just need to find 4 key values: the highest row that has a 1, the lowest row, the column furthest to the left, and the column furthest to the right. Once we find these 4 boundaries, the problem becomes much simpler. Let's walk through an example. Imagine we have this 2x3 grid. We'll scan through it looking for ones. The first one we see is in the top row, at column 1. At this point, our top, bottom, left and right boundaries are all set by this single cell. But then we find another one, in the second row at column 0. This one is lower down, so we update our bottom boundary to row 1. It's also further left, so we update our left boundary to column 0. Finally, we see a 1 in the second row at column 2. This is the rightmost one we've seen, so we update our right boundary to column 2. After checking everything, we have our final boundaries. Now that we have the boundaries, calculating the area is straightforward. The height isn't just the bottom row minus the top row. We have to add 1 to be inclusive. So for our example, the height is 1 minus 0 plus 1, which gives us 2. Similarly, the width is the rightmost column minus the leftmost, plus 1. That's 2 minus 0 plus 1, which is 3. Finally, the area is just height times width. 2 times 3 equals 6. And that's our answer. So the official approach is exactly what we just did. It's called a one-time traversal. We'll create 4 variables to keep track of our boundaries: a minimum and maximum row index, and a minimum and maximum column index. Then, we'll just loop through every single cell of the grid one time to find these values. Alright, here's the full Python code for this approach. It might look a little dense at first glance, but it's doing exactly what we discussed. Let's break it down piece by piece so it's super clear. First, we set up our variables. We get the number of rows and columns. Then comes the clever part: initialization. We set our minimum row and column trackers to values that are guaranteed to be larger than any valid index. And we set our maximum trackers to 0. This way, the very first time we find a 1, its coordinates will automatically become our initial min and max boundaries. Next up are the loops. This is just a standard way to visit every single cell in the grid, row by row, column by column. Inside the loops we have a simple check. If the value at the current cell is 1, we update our boundaries. For example, the line for min I says, take the smaller value between the current min I and the current row I. This ensures we're always tracking the absolute minimums and maximums across the entire grid. And finally, the return statement. After our loops have finished, we'll have the correct final values for our 4 boundaries. We just plug them into the height and width formulas we talked about. First, we calculate the height by taking the max row, subtracting the min row, and adding 1. Then we calculate the width by taking the max column, subtracting the min column, and adding 1. Finally, we multiply those 2 results together and return the area. Now, what about an edge case? What if the grid has no ones at all? With the current code, our update logic would never run, and we'd be left with our initial invalid boundary values, leading to a weird result. The problem constraints say there's at least 1, but it's good practice to handle this. We can add a simple check. If our min I variable never changed from its initial value, it means we never found a 1. In that case, the area should be 0. So how efficient is this solution? For time complexity, we have to look at every single cell in the grid, so it's big O of m times n, where m is the number of rows, and n is the number of columns. We can't really do better than that, because anyone could be anywhere. For space, it's fantastic. We only use a handful of variables to store the boundaries, regardless of how huge the grid is. That gives us a space complexity of big O of 1, or constant space. Alright, let's wrap up with the key takeaways. The main idea is that this seemingly complex area problem is really just about finding 4 numbers: the top, bottom, left and right boundaries. We can find these efficiently by making a single pass through the entire grid. And a little bit of clever thinking on how to initialize our boundary variables makes the code work smoothly from the very first one it finds. I hope that breakdown was helpful. If it clicked for you, please hit the like button, and maybe subscribe for more explanations like this. If you have any questions or a different way to solve it, drop a comment below. And hey, if you're feeling extra supportive, you can always contribute to the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next one.